Okay, yeah. Thanks. So this talk is a little bit different from the previous talks, obviously for the reason of being a perspective paper. But I hope that some of the ideas, although I haven't validated, but could be potentially validated by some of you in the future. So let me start with my perspective of understanding the large language models by making a connection with the traditional language models and try to explain why I think these large language models are very powerful. So I summarize some of the differences here, but the objective function is actually similar to model sequence of words or any tokens. Now, in the case of traditional language models, we tend to have models that have interpretable parameters, a lot of parameters, that would encode essentially surface patterns. And so the model essentially literally memorizes superficial patterns. One word follows another, etc. Right? So in the case of bigram language model, I showed a picture here. We essentially just draw all the edges. If you think about the bottom part as input and the top part as output, we want to predict the probability of retrieval given information. And so this is directly retrieved, looked up. Right? Now, so this kind of representation is very inefficient. It's redundant. We have words, information, and data. They're very similar, and their properties in terms of what kind of words will follow will be very similar, and yet this kind of models don't capture that. So it's an inefficient way of representing the information, and it doesn't generalize well. Right? But in contrast, if you look at the right side, that's how a neural network, deep neural network, would represent this kind of model. And the bottom and the top are the same, but in the middle, we kind of have more detailed modeling of their relations with, I showed 2 layers, but potentially there could be more layers. Right? So as a result, these parameters are no longer so interpretable, especially in the middle, we can no longer interpret those edges, even though there are weights there. Right? But it's a more compact representation of the information. And more importantly, it's generalizable, meaning that the representation here would allow us to handle unseen data. In the old case, if I happen to see one word following another, we have to use ad hoc smoothing methods to deal with that. Right? So, but here, since they are all compressed to be represented in latent vector space, then you actually can compute all those probabilities, because these models construct the probabilities by using elementary patterns that are also memorized. Okay, so now if you look at the parameter size, there's a clear difference here. We here for just bigram model, not to say trigram, we already have the vocabulary size squared. So it's a lot of parameters that are not efficient. But if you look at the neural network representation, it's much smaller. Right? K is the number of hidden nodes. Here, I assume these 2 layers have similar number of neurons. So you can see the parameter space is actually more compact, yet it's more generalizable. Actually, it's precisely because of the compression that has caused it to generalize. If you had given it more parameters and to allow the network to literally memorize everything at the surface level, it's not going to generalize just like the traditional models. Now, technically, why would this kind of networks effective? Why do we see these large language models that are fluent in understanding our language and being able to generate fluent text? I think there are 2 major technical reasons, and maybe a third minor reason that's also important. The first is, I call it horizontal compression. That means if you look at the network, we now have K nodes in the middle, or everything has to go through only K nodes. Before they can be connected to everything, you can memorize that. But once you are forced to go through K nodes, it forces clustering. It's going to pick up the similar paths, like data and information, will likely be grouped together to form some kind of concept. I call it the retrieval object. Perhaps it may not be interpretable. If in our language there's something referring to that concept, it will be completely interpretable. Right? So this is the efficient way to optimize the objective function. Right? You have to cluster the paths from the left that are similar. So you force them to go through the same path in the new representation. So this leads to concept formation. Like data and information or cat and dog, they will be forced together into some kind of abstract concept. It allows the model to learn a concept, and therefore it can generalize to future instances of the same concept. So once you know another animal is connected to the same concept animal, everything else will be the same, right? The second reason is vertical stretch, and this is a deep learning part. A deeper network further forces the function between the input and the output to be decomposed into more elementary elements, elementary patterns. Now, again, this example could illustrate this point. Here, for example, once we have retrieval objects, I could associate this with retrieval or other kind of words on the top directly. I don't need to go through the second layer. If I hadn't done that, then I would have association of retrieval object directly with retrieval. But if I'm using the current network that has a further latent layer, what's going to happen is it's going to further decompose this relation, or it's going to explain this complex relation with additional concepts, especially concepts that can be shared in other tasks. For example, I'm imagining this, right? There could be some node or set of nodes or some distribution represent the notion of a collection. Because in order for something to be retrieved, and there's some notion of collection. There's something like a query. Someone needs to get access to the data or information. Something like that will be represented. And maybe something related to retrieval or access, and that kind of things cluster. So this kind of vertical stretch allows to decompose a complex function into more elementary reusable functions. Note that the horizontal compression will force any intermediate steps to be reusable, right? So generalizable. So this allows it to learn these elementary association patterns. Now these will allow it to do limited reasoning, because in the future, if you want to go from A to B through this network, it has to go through those steps. Right, so it needs to be able to do that. And if it can successfully go through those steps, it will give you an answer. It will generate the answer that as if it has done some reasoning here. This is the second reason. Now, if you have these reasons, now you can see it actually can understand the content much better. Think about the phrase like a banana retrieval. Normally, it doesn't make sense. But if you use this kind of network to fit this kind of pattern, what's going to happen is that it's going to interpret the banana as something like a retrieval object in order to maximize this probability, in order to make sense of it. So it will force banana kind of go through this kind of retrieval object. Normally, the probability is very small, but in that context, if it needs to be done, it would have that interpretation. Right? So this example shows these two kind of, I think, technical elements that have made these models essentially being able to understand the semantics of language and being able to generate a fluent and meaningful text. The third element, which I think is minor, but is also very important, that's in the transformer architecture, which doesn't have to be the only architecture, I think. And the self-attention allows parallel, efficient learning of structures of elements. So I use the bigram model as example. But bigram has just one input. What if it's trigram? Then I have two, and you can think about the context with maybe 10 words or even more. When you have that kind of content, then you have to learn the patterns, the structure among them. Right? Some are closer than others. Think about the pause structure, sentence structure. Now that structure can be picked up by using this self-attention efficiently. I say that's a minor, reason. It's because there are alternative architectures now proposed by people, and it doesn't have to be the only way to do that. But I think the number one, number two, this kind of compressed and then deep learning is quite important, and those are the reasons why we are able to have this kind of large language models now that are very powerful. Now I have to say that I think traditionally there are some techniques that are actually pointing to these directions, not at this scale. Latent semantic indexing actually is a way to move toward embedding representation. And if you think about one layer, neural network with words as input and words as a document as output, or the other way, you essentially have a matrix factorization of the matrix and into multiple submatrices, and to give you a dimension reduction. And that's exactly the same. But here we're talking about the multiple matrices that will be together, multiplied together to explain the relation, the complex relation. And I think, n-gram class language model, where you try to model a latent class of words and then try to do smoothing is another example. Those are all ideas toward this direction, but neural network gives us a unified framework, very powerful, very general, that can be trained also on using a general toolkit that has accelerated this kind of development. But of course, you also need to have a lot of data to learn those in latent representations. So I spent actually quite a bit of time to talk about this perspective, but I think this is why I have made the conclusions about the following questions. So with that perspective, I'm going to address some high-level questions. The first is, how can we use these models to improve the current search engines? And then, would this kind of models significantly impact the future retrieval systems? What are the opportunities to transform information retrieval? And then what are the major challenges? And if you think about it really into the future, it's 10 years, 20 years, even longer, what would happen to information retrieval system? Would we still have search engines, or maybe these models will replace search engines? Now, so I go one by one. I mostly will highlight some of the perspectives that are somewhat unique, maybe, or more interesting, because you can read about other things in the paper. The first is about the current search engines. There has been a lot of work already done, including the work you have already heard, right? So, and at this conference, there's a lot of great work that has tried to use large language models to improve the current search engine. But my perspective is from this ideal query hypothesis. This was originally proposed by David Lewis in his dissertation. And the idea here is, well, the hypothesis says that for any information need, there exists an ideal query with the right keywords. And if you use that kind of query to do retrieval, simple retrieval systems will give you relevant documents on the top, at least one of them, right? So now, with that hypothesis, I think there's a great opportunity of use large language models to improve the query side. So if you think about search engine user collaboration, how do we optimize the performance? You can optimize search engine, but you can also optimize human intelligence. That's the point Nick Belfin pointed out when we talk about intelligent information retrieval, but whose intelligence? Now here, large language models would be able to perhaps formulate a much better query. If we can do that, then the search engines don't have to work that hard. So that's the main point. Now this slide shows the analysis of the current search engines, their pros and their cons. Right, so they are working well for a lot of queries, popular queries. We're using those engines all the time, and we're used to those engines as well. To some extent, we trust the retrieval system, and we're willing to look at the document from some site and judge the quality and get the answer. But of course, we also know that for a lot of long-tail queries, the search engine doesn't work well. And those are the queries that are somehow unique, and then the user has a vocabulary gap, typically in complex information needs, like medical search, or finding a complex product, a product with complex specification. Those are actually not uncommon, because when users want to use a search engine, that's often because users want to learn about something the user will have some knowledge gap. And that's the main reason why the current search engines don't work well yet. Other cases are vague information need, like I'm buying a gift, but I'm not necessarily clear about what to buy. That's not the fault of search engines, but search engines could potentially help them. Search engines cannot help us digest results, and also support only limited interaction. Now, of course, all these limitations could be fixed by using large language models, expand the query, expand the document, bridge the gap, or ask clarification questions, understand the user's response, and then modify the search accordingly. And I think search engines are already using these large language models to summarize search results, support the question answering context. But mostly, I think large language models will enable conversational search and recommend system. So there's an excellent report that I cite here where you can find more discussion of ideas here. But I want to then move to the futures information retrieval system. How do I define the future, the boundary? Well, there's no clear boundary. I mostly thought about that as some system that's dramatically different from the current system, and that is a conversational search and recommended system. And my perspective would be from the retrieval model perspective. Right, so if you think about the general opportunities of those large language models, what are the new capabilities we have today? Well, they are able to understand natural language. So that means they can be used to improve interface for any device. Right? So you can talk to your refrigerator in the future in natural language, presumably it can understand that. Right? And they can generate the text. They can do a lot of tasks that we couldn't do before. They can do question answering. They can generate literally a lot of useful text that people are already using. And they can be fine-tuned to perform new tasks. So there's a huge potential. But from our perspective, I think that just means users in the future should be able to directly express their information in natural language. Right? So and then the search engine could also explain the search results more clearly in detail, and then explain the ranking and help users learn about those specifications, make decisions between different choices. And they can be also adapted through search logs, to do fine-tuning through search logs to learn relevance. Essentially, they can support the general conversational search and recommender system. The question I ask here is how can we develop then a new generation of generative retrieval model for this kind of conversation? Now, this is what we have today, right? We match a query and item, and we try to assess relevance in recommendation and search. We're all doing that. Now, if conversation is at this level, you can change the ranking. You can talk about the different documents or different query. The conversation really cannot go in depth to improve the matching. What we need is to decompose this relevance into detailed matching of attributes. So for information needed, like a laptop for travel, and then you need to kind of figure out the needs. That it has to be easy to carry, etc. It has to be a laptop, and then a particular laptop can then be matched with that kind of need based on attributes. Right, so this level is needed because then we can have conversations about this, can modify the system's understanding of users' need. Now, mathematically, they can be written in these formulas. This is just to use probabilistic terms to say what I just said. Right? So decompose the matching probability into some kind of sum over all the possible needs, and then you just and then model the attributes of a need, and then model the attributes of items, and then model the matching. So a main point to be made here is that we need, in order to effectively support the conversational search and recommendation, we need a model to scaffold this kind of conversation. Knowledge graph could be used as well. Here I'm just showing a step toward that goal by refining a general retrieval model. Here. Once we have that, a user could be able to say, hey, I actually don't mean to prefer that value, so in some kind of attributes. And then you modify that, you improve the understanding of user's intent. The same model can be used for recommendation by dropping the query. Everything else is the same. Now, what's also more interesting is that this could be regarded as an interpretable neural network. So I put this query user and context at the bottom, and the item on the top. And then if you use this kind of model, like a neural network, to compute the scores, and you will recover the probabilistic model on the previous slide. So the model can be computed in this way. But more interestingly, then you can train this model in the end-to-end manner. Right? So these are just the simpler networks, but interpretable than neural networks, but you can do the same thing. But of course, if you do that, you will suffer from the traditional models, the sparseness, the lack of generalization in those ages. So what's more interesting, I think, is to move toward a neural symbolic architecture, where edge could be replaced by a sub-neural network. One node could be replaced by a set of nodes. So for example, the query is laptop retrieval, and you want to match a Lenovo laptop like this one. XY is my laptop here. So it has some attributes. Now, search log has such information. You can learn the model to associate with them, right? So, but that's not as effective as if we infer, the intent. That's a laptop suitable for traveling, and furthermore, it should be easy to carry and it should be a laptop. If you actually stretch this by adding another level of neural network anywhere, you will force to learn detailed knowledge. For example, here you might then learn that in order to be easy to carry, it has to be small, has to be light. And then 3 pounds of laptop is regarded as light. etc. Now, the reason why this decomposition is important because they can be generalized. For future queries, if you want to have something for travel, it will know as long as it's easy to carry, and the concept of easy to carry in a different category may be different, but you can see the knowledge pieces are learned here that can be generalized. Okay, looks like I'm using a lot of, is this the end of the talk now? Let me rush this through. The major challenges, I think, obviously, since these are refinement of classic models, so the important question is how do we use these models to estimate the probabilities? They can, in the paper I showed that you can estimate all those 4 components by using large language models. But a more, I think, broad question is how do we integrate the large language models with the existing search engines to model the relevance and to optimize the efficiency, the cost also. And how do you support the retrieval augmented generation, or more generally, retrieval assisted agent? How do you combine question answering with search? I think many years ago, I think Jamie Cannon talked about some of the ideas about the rack here. At that time, I vaguely remember, today I just verified, it was just like that. It was pointed out that search engines would be able to support some tasks like QA or natural language processing tasks. And then it's quite related to the recent work here. So very quickly move to the last question. It's really about long-term impact of these models. Would search engines disappear? Now, my conclusion is that they won't, and the reason is very simple. The current ChatGPT models are doing a closed book exam. When you ask it to solve a problem, answer a question, it relies on its memorized knowledge to do the work. It doesn't know how to look up information on the web. As a result, if you ask the model what's the weather today, or you want to know just because it has not been given the data. And OpenAI cannot possibly feed the data instantly. So what would happen then? Well, they have to use a search engine. Right? So they should move to an open book model, where they are allowed to look up not only search engine and using search engine, but using database system, using any tool here. And so it's an open book environment. Now, just like when we are preparing for exam in a closed book environment versus an open book environment, we use different strategies. These large language models would need to do the same. There's no need to memorize all the weather data or those data that you can easily look up using a search engine, but instead you need to learn generalizable knowledge that can be applied in the future. So I think these large language models will never replace search engines for these reasons. And future models actually would have to learn how to use search engines on behalf of users to solve a problem, perform a task. Right? So the search engines could be external, could be internal to the model, but search engines will be there. And so there are 2 kinds of interesting questions. How can search engines best support large language models instead of human users? That's a big class of questions. How can a large language model optimize its performance in an open book exam, meaning that its objective function needs to consider some tasks can be easily solved by using search engines. So it should be a reinforcement learning kind of model that would guide the language model to optimize its training. So I think this picture shows what would happen likely in the future. In the direction of large language models, I predict that the current generation non-explainable large language models will likely become more explainable as neurosymbolic kind of AI makes more progress. And then eventually these large language models will be able to actually adjust their reward function, be self-motivated. Now, what does that mean for IR then? Well, currently, because they are not explainable, they are not trustable, so they should be supporting our current technology. They cannot directly interact with users. The risk is too high. The error has a high cost. So this is large language model assisted retrieval stage. And they are below our existing technology. But once they are more trustable, they can interact with users directly, then retrieval system becomes a supporting tool to those agents, so I call retrieval assisted agent. Now, what would happen when they are really, like a human, the AGI, era, then I think retrieval likely will be absorbed into the agent, meaning that inside the large language model, it has some mechanism to do search, to validate information, to find the provenance, etc. So I think I'm going to just stop here, and the summary just shows all the takeaway messages I already said. Sorry for running over time.